I will be very careful the next time I move that. Okay, so carbon can come in two different common forms. Can anyone tell me what the common forms of that we see in our everyday life are? Yeah, carbon. So I'm talking about just the pure element. Do you know what two things that are pretty common substances? Soda. What? Charcoal. So graphite. Graphite. So charcoal is impure. It's like a mixture, but the carbon that's in charcoal is graphite. So graphite, also in your pencils, is pure carbon, and it is bonded in a particular way. So one of them is graphite. Carbon can also repeat in a different way, bond together in a different way to make something that's you can use in jewelry. Diamonds, excellent. So diamonds and graphite are both naturally occurring forms of carbon. And the only thing, the difference between them is that the graphite over time under pressure the carbon atoms will move and bond in a different geometry. So those are two pure elements. Those are examples of elements. So you can have one element that can come in different forms. It's still just carbon. Now there are a number of elements that, just like oxygen, we call them diatomics, and those are H2, O2, F2, Br2, I2, N2, and Cl2. Once again, still an element because there's only one type of atom in each of these molecules, but they just like to pair up. And the way you can remember this, there are two ways. The way I remembered it is, think of the word Professor Hofbrinkel, if you anyone has heard that. It's just spelled out Hofbrinkel. So it's just it's like the name of a fictional chemistry professor. But if you remember the word Hofbrinkel, other people have heard Brinkelhoff. The other way is the rule of 7. And that's if you look at the, let me just find this photos. If you look at, the periodic table, the rule of 7 is you have a 7 right here, and then you have hydrogen over here, which is a little awkward. But so all of these are diatomics, and you'll get a periodic table on your test. You won't use it extensively on this test. You will use it more on the next ones. But so these 7 elements come as diatomics. You do need to know that. Okay, so diatomics just means 2 atoms. diatomics. Okay, now let me go to whiteboard. Okay. Now, I had matter. Okay, pure substance. So we already have the pure substances. We have elements and we have compounds. Now on the other side, we have mixtures. Can anyone give me an example of one type of mixture that you've heard of? Huh? Hydrochloric acid is a mixture, but what type of mixture is it? There are 2 types of mixtures. Have you ever heard of a homogeneous mixture and a heterogeneous mixture? Homogeneous mixture, does anybody know what that is? Yeah, it's a uniform mixture. It's mixed on the molecular level. So yeah, a uniform mixture, it's basically where you can't really see a divide between the 2 things. The way I like to describe it in this class is basically if you have a piece of tightly woven cloth and you pour that mixture through, if it's liquid, you wouldn't leave anything behind in terms of like chunks of solid or things like that. So for example, if you have salt water and it's well mixed, that is a homogeneous mixture. However, if you oversaturate salt water and there's stuff on the bottom, if you pour that through a piece of cloth, you'll leave that solid behind. Okay, so think of it as it's not easy to divide that because you have a really well mixed, it's very well mixed mixture. And so these are things like salt water, if it's not not oversaturated. Tea, because when you soak a tea bag in tea, you allow the caffeine molecules and the other molecules from those tea leaves, those extracts, they go into the water and they mix very well. And then you have also things like you don't necessarily have to have a liquid. That's the most common type. But things like alloys, metal alloys, are technically mixtures because they are two different types of metals that are mixed together. And you have, for example, in steel, you have iron and then you have carbon every so often, and it is uniformly mixed across that alloy. So things like alloys. And then also air, I would call a homogeneous mixture. It's not always the case in terms of like our stratosphere, way up in the stratosphere, there's not as much oxygen and stuff like that. But as we're breathing in this room, it's generally the same well-unified mixture of nitrogen, oxygen, CO2, and other gases. So I consider air a homogeneous mixture because it's not like we have, a bunch of CO2 sitting in this corner and a bunch of nitrogen sitting in this corner. It's pretty well mixed. So there's the homogeneous mixture, and then we have heterogeneous mixtures. This is something that is not well mixed. Cereal is a heterogeneous mixture because you've got pieces of solid cereal and then you have milk around it. That's not well mixed on the molecular level. Can anyone ever give me any other examples of heterogeneous mixtures? Salad. What? Trail mix, another heterogeneous mixture. What if you go to an Italian restaurant, they give you something at the beginning when you first sit down, olive oil and vinegar. Even though they're two liquids, they're not miscible, means they don't mix well. You can see there's chunks of that and chunks of that. So you olive oil and vinegar is a heterogeneous mixture. It's not a uniform mixture. Also things like orange juice with pulp, if you pour, for example, if you poured orange juice with pulp through a piece of cloth, you leave solid pulp behind, things like that. Yeah, I think that's all I want to say about homogeneous and heterogeneous. Note that this is not homogeneous. It actually has an extra E in it. The word is homogeneous. Homogeneous is a very similar term, but it's used in the social sciences like a homogeneous society, things like that. So we're talking homogeneous is the correct chemistry term. Any questions on this? I might ask you to identify something as a pure substance, pure compound element, heterogeneous or homogeneous, or I might ask for examples. So I would say, give an example of a heterogeneous mixture. And you could say like chili or salad or cereal, something like that. You can also have a heterogeneous phase mixture. This is kind of its own little definition. Now this is important because what if you have something like ice water? Technically, in terms of chemical composition, that's a homogeneous mixture because it's either liquid H2O or solid H2O. But you have solid and you have liquid. So that is a heterogeneous phase mixture. So something like ice water. Cereal is also an example of this. Then there are things like cereal's an example of this. Also, soda is a heterogeneous phase mixture because you have liquid and you have gas bubbles that they're not uniform on the molecular level. Cereal and soda are also examples of heterogeneous composition mixtures because in soda, the bubbles are CO2 and the rest is sugar water. In cereal, the hard stuff is grains and stuff, and then you have milk. So you can have something that's both a heterogeneous phase mixture and a heterogeneous composition mixture. While ice water is just a heterogeneous phase mixture. Do you see the difference there? Did I hear a no? Okay, so it's like, hold on one second. Soda is heterogeneous composition mixture as well. Okay, so if I have ice water, we have solid and we have liquid, okay? So those are different phases. So you're mixing two different phases. And because there's a chunk of solid and there's chunks of liquid, right? That's a heterogeneous mixture. It's not like, I think it would be hard to have like a homogeneous phase mixture, but we're talking about how you have parts that are solid and parts that are liquid, okay? But they are both H2O, right? Ice is just solid water. In soda, so this is ice water, H2O. In soda, you have bubbles that are CO2. And then surrounding them, you have sugar water. So the bubbles are not only a different phase, they're gas versus liquid, they're also a different type of molecule because you have CO2 here and then you have sugar water here. So not only are the phases not mixed, the chemicals here, the molecules are not uniformly mixed because you have pockets of CO2 and then you have pockets of sugar water. Are we clear on that now? Yeah. Okay. Cereal's the same way. So this is soda, and then cereal. I'll draw a bowl for this one. So like say you have a Lucky Charm, right? So the rainbow is a marshmallow and it's solid. The liquid is milk. So once again, you have a solid and a liquid, and then milk is made up of very different molecules than the marshmallow. So not only are they, what's up? Exactly. Phase is the state of matter. Yeah. Yeah. So is oil and vinegar are yeah, oil and vinegar is a heterogeneous chemical mixture, a composition mixture, but it's not a heterogeneous phase mixture because they are both liquids. But what I'll just ask you for is I'll say, give me a heterogeneous mixture, and then I'll specifically ask you for a heterogeneous phase mixture. So that would be like soda, cereal, but cereal can also be your heterogeneous, just normal heterogeneous mixture as well. Yeah. Yeah, so phase is solid, liquid, gas, okay? So if you have something that is a mixture of solid and liquid or gas and liquid, that is a phase mixture. However, if it's just a mixture of so in olive oil oil and vinegar, it doesn't mix well. That's a heterogeneous composition mixture because olive oil is made up of different molecules than vinegar, okay? And then you can have something that is both a heterogeneous phase mixture and a heterogeneous composition mixture because sometimes you have the phase is, for example, the gas in soda, which is CO2, which is a different chemical makeup than the liquid part. Okay. I have to move on from this, but we can talk about, if you have any more questions, you can ask me. You can talk to the tutors on Sunday. You can talk to me during discussion on Monday. Or we can also bring this, Tuesday is a review session in the class. So also bring questions that you have to that session as well, to my lecture. Sorry, Wednesday. Sorry, I always talk about Tuesday. It's Wednesday. Okay, chemical change versus physical change. A physical change is one in which matter changes appearance, but not chemical makeup. Can anyone give me an example of a physical change? Ice melting. So phase changes are physical changes because when ice melts, it doesn't become a different molecule. You don't break any bonds. You're just turning liquid from, you're just turning solid water, solid H2O, to liquid H2O. So melting, boiling, anything else? Freezing, yes. So there are different other kinds of physical changes too that don't have to do with phase changes. What? That's a physical property, and we'll talk about that. But what's a change that can happen? If you break something, are you changing its chemical makeup? You're just breaking it. If you bend something, not necessarily changing its chemical makeup. Any other examples? Sorry, what? Cutting, yeah, so cutting. Yeah. Now, a chemical change results in new chemical makeup. So what you're dealing with changes its chemical makeup. Can anyone give me an example of a chemical change? Burning, combustion. Combustion is a chemical change. What else? Corrosion, yes. Corrosion is oxidation of metal, otherwise known as rusting, if you're dealing with iron. Anything else? Cooking and baking. Last night I asked the class, I was like, what do you do to feed yourself? And they were like, chewing. I was like, that's not, I was looking for cooking, but you do chew. So cooking and baking, those are chemical changes. Decomposition, and then there's also, if you have a color change, it tends to indicate a chemical change. Not always, but often. For example, if I get sunburnt, you see a color change, and that's because the sun has created a chemical change in the cells of my skin. Okay, so fading and color change due to oxidation or UV exposure. So a color change can be an indicator of a chemical change. Often physical and chemical changes will happen pretty rapidly in series. For example, if you cook with a gas stove at home, so the gas generally starts out in the container, it's highly pressurized, so it starts out as a liquid. Then you release a little bit and there's a phase change between liquid and gas. So you've had a phase change. Then you light it on fire. That is a combustion, that's a chemical change. So right there in series, you have a physical change that then creates, that then allows for a chemical change of combustion. Any questions on this? So in tandem with this, we also have chemical versus physical properties. And Elliot said earlier that color is physical, and it is. I just said that color change can be indicative of a chemical change, but color itself is a physical property. And the reason for that is a physical property can be demonstrated or is demonstrated without undergoing a chemical change. Now, what do I mean by that? When you look at this folder, it's purple, but there's not a chemical change occurring to tell you that. Can anyone give me another example of a physical property? Physical property. Shape. Anything else? What about mass and density? Right, to tell how heavy something is, you don't have to light it on fire, right? You can just hold it. So mass, density, what did you say? Size, texture. Now, based on the fact that we said that boiling and melting are physical changes, are boiling point and melting point physical properties? Yes, because you don't have to, when you boil something, that tells you what the boiling point is, but you're not doing a chemical change to determine the boiling point. So boiling point, freezing point, things like that. A chemical property, on the flip side, it must undergo a chemical change in order to be demonstrated. For example, you can't tell how flammable something is until you light it on fire. So, demonstrated through chemical change. So, flammability. Can anyone think of another example? What? Conductivity. I think that's what would you say that is? A physical property? Because I don't, see, that's kind of a weird one, because conductivity is just the movement of electrons, which you can, or like, it depends on your definition. I would stay away from, yeah, I would stay away from that one. That's kind of like on the edge. What about toxicity? You don't know how toxic something is until it reacts with your body. Also, acidity. Corrosivity, how easily a metal corrodes. For example, gold has really low corrosivity. Iron has really high corrosivity. But you don't know that until you expose them to oxygen. I would say taste is a chemical change because you technically have, there are chemical reactions happening on your tongue when you taste things. Smell is once again kind of on the edge, but I would probably, you have sensors. I would say that smell is a physical property, but it's those ones are a little hard. Those are kind of on the edge. So just like there are certain things, like for example, tar is kind of on the line between solid and liquid, right? So if you look at tar, it stays shape for a while, but over time it can slowly form to its container. There are also things that are on the edge of chemical and physical properties and chemical and physical changes. Do you have a question?
Is there like how do you measure?
Yeah, so viscosity is kind of a measure, like that's kind of the line that can kind of define the line between solid and liquid, because if something is super, super viscous and it doesn't move at all, but over time it is like slight, it's, you know, it can fill its container. I mean, if you are a scientist working on that edge, you might have a definition. But we generally, you'll find out in this class that often we kind of draw arbitrary lines between, okay, this is a solid, this is a liquid, and things kind of can happen on the edge. And for example, something that's super viscous, like tar. So, I mean, and you can use viscosity as a measure of whether it's solid or liquid. That's a possibility. But we won't be talking, but I would say viscosity is a physical property because you don't have to make it undergo a chemical reaction. So viscosity is a physical property. I know that wasn't your question, but brought up another physical property. Sorry, viscosity with a Y there. Any questions so far? Where are we at? Okay. I want to talk about energy, because all these physical and chemical changes involve exchanges of energy. Does anybody know what energy is? The definition? Kind of a physics term. It's kind of a physics definition. It's the ability to do work. Now, the question is, what is work? Work involves force that is acted upon something, okay? Which, if you think about work in terms of a car, it takes work to move the tires. And in order to do that, we need the energy that comes from combusting the fuel in the engine. I can't push on something if I don't have the energy to do that, right? So I can't push on this wall if I haven't eaten in 3 days and I'm really weak. So everything that involves work does take energy. So you can think about this on the human level of cars and pushing on walls and stuff like that, but it also is true on the atomic and molecular level. What are the two types of energy? What makes up total energy? Anybody know? Physics class? Two types of energy. Potential and kinetic. Ke and Pe. So what is kinetic energy associated with? Motion, movement. And I heard back there, that's actually potential. What did you say? Position. So potential energy is associated with position. And also in chemistry, it's associated with composition. And I'll explain that a little more. But in terms of position, for example, there's all the time we have an interchange between kinetic energy and potential energy. For example, if I hold this pen here, it has a lot of potential energy because of its position. If it was on the floor, it wouldn't have as much potential energy, but because it's way above the floor, it has potential energy. Now, when I drop it, that potential energy turns into kinetic energy of that movement, and that kinetic energy is released. And then it has no potential energy. So there's a lot of interchange in our universe of kinetic to potential and vice versa. With composition, every single bond in a molecule contains some energy. And when you break that bond, you release energy. And when you release energy, it often comes out in the form of heat or light. That is the potential energy of the bond turning into the kinetic energy of heat or light. Now, when we have two types. This exchange can go in two different directions. We can have energy going into the system or energy coming out of the system, or the reaction. Does anybody know what it's called when the system releases energy? Exothermic, excellent. So energy and time. In an exothermic reaction, we start with, or an exothermic change, because physical changes can also be exothermic. We have reactants that have high potential energy. Often that means they have a lot of energy stored in their bonds if this is a chemical reaction. We have products that have low potential energy, which means that change there, that energy has to go somewhere. It is released as kinetic energy into its environment. So we have this exchange of the environment and the system. The what we call the delta E, the change in energy, this kinetic energy that's released, is from the point of view of the system. The system loses the energy. So for example, when a fire is an exothermic reaction. The fire, the things that are burning, the reactants that are burning, so the wood, that's the energy. That's the system. The air around it is the environment. If you're standing by the fire, you can also be part of the environment, because when that system releases the energy in the form of heat, you get some of that heat. You are the environment. The system, which is the wood, those reactants, and going to the products of the ashes and H2O and CO2, that is releasing heat that heat is given to you. You are the environment. The fire is the system. The products and the reactants are the system. Does everybody get that? So, an exothermic process is something that releases heat or light, and burning is one. Can anyone else tell me another exothermic process? Nuclear fusion. would be, yes, I believe that is an exothermic process. What? Yeah, that's usually combustion. So combustion, fuel consumption generally is combustion. Yeah. But then you have, you have nuclear. But the reason we have like fuel, generally the processing of fuel to give us energy, that is inherently an exothermic process because we're trying to get that energy from the fuel. Another example is actually freezing. Okay. And you might be like, well, exothermic processes generally feel warm, right? Like fire, fuel consumption, combustion. However, freezing, think about what I said about states on Wednesday. Which phase, what state of matter is higher energy? Gas. Which state is lowest energy? Solid. When you go from a higher energy phase, such as liquid, to a lower energy phase, such as solid, that system is losing energy. It's released into the environment. So when water goes from liquid to solid, that energy that it is losing has to go somewhere, goes into the environment. So that is an exothermic process. The reason we don't feel it being warm is because it's in a freezer. But have you ever felt the back of your refrigerator? It's really hot. The heat has to go somewhere. So when things are going from gas to liquid or liquid to solid, they're going down in energy. So freezing and condensation. Corrosion is also an exothermic process. It just happens very, very slowly over time. So because it only loses small amounts of heat over time, we don't really feel it, but it is an exothermic reaction. Does anybody know what the opposite type of reaction is called? Endothermic, excellent. So endothermic process. Can anyone give me an example of an endothermic process? Well, reactants in an endothermic process start at low potential energy. They take heat from the environment or take light from the environment. So kinetic energy is absorbed and the products are higher. Boiling is one. Because you're starting with a liquid, lower energy state, get to a gas, higher energy state. You have to put in heat to boil something. So boiling and also melting. And if you look at this, these are opposite processes. Freezing and melting are opposite processes, which means they're endo and exothermic opposites. Same with condensation and boiling, opposite processes, which means that one takes in heat and one gives off heat. I always like to think of like the condensation. Has anyone ever had a steam burn? It's a really bad burn. And the reason for that is if you put your hand over boiling water, that's water vapor, okay? Steam is gas phase water. It hits your hand and immediately condenses, and it releases a whole lot of heat in a very short amount of time, which is why it's so painful. So if you think about that, it's in a higher energy state, it hits your hand. Your hand is the environment. So the hand receives the heat that is being released as that steam goes into liquid form, as it condenses on your hand. Opposite process, when we sweat. Sweating cools your system. And the reason for that is, if you have droplets of water on your skin, if they go into gas form, they have to take heat from somewhere. They take it from your body. So the heat from your body, which is the environment, goes into the system, which is the water on your skin, creating an endothermic process, liquid to gas evaporation. Everybody see that? Okay. Another type of endothermic process is baking, cooking. You have to put in heat to make those changes happen. Depends on the chemicals. If it's water and acid, it feels hot. Yes, that's releasing energy into your hand. However, if you break one of those ice packs and it turns cold, that's sorry. Water, yeah, so water and acid is exothermic. And if you break an ice pack and it turns cold, that's endothermic, because what it's doing is it's the two chemicals in there are reacting and it's pulling heat from your skin, from your body, from the environment. Okay, so cooking, baking, and also those ice packs. Yes, so the environment, so the system is the chemicals that are doing the chemical and physical change, the molecules that are doing the change. For example, water is going from liquid to gas. So the water droplets going from liquid to gas are the system. From their point of view, when you put in heat, they're gaining heat. So that is an endothermic process. Anything, so, and that it's taking heat away from your body, so that is, your body is the environment. Yeah, it's the molecules that are undergoing the chemical or physical change are the system. What surrounds it is the environment. So sometimes that's your body, sometimes that's just the air. Sometimes that's metal. A metal conducts heat really well, right? So if you have a reaction happening in a metal vessel, that heat is going to go into the metal. You can also think of in bigger systems, for example, overall, going on a run. Biological systems get very complicated because there's tons of reactions happening all the time. Some of them are endothermic, some of them are exothermic. But overall, as you go running, you are expending energy into the environment. In that case, the overall process that goes on in your body is you are losing energy. So in that case, your body is a system, and then you're losing that energy to the environment. So it really depends on what you're talking about, but the gaining and the losing is always from the point of view of the system. Everybody okay with that? Okay, let's talk about how we measure thermal energy. Temperature is how we measure thermal energy. Does anybody know what thermal energy is on the fundamental level? I sort of talked about this on Wednesday. Vibration of atoms. Yes. So your temperature is how you measure the speed at which the matter is vibrating. So measure of thermal energy, which is vibration of matter. We get into some semantics here between like temperature, thermal energy, heat. So thermal energy is the vibration, heat is the transfer of that energy, and then temperature is how we measure it. So they are all different things. I'm just gonna have you, I just want you to know that temperature is how we measure thermal energy, how much thermal energy something has. The more thermal energy, the hotter it feels to us. What are the metric units of temperature? Celsius and Kelvin. And what's the English version? Fahrenheit. if any type of measurement like sort of doesn't make sense, it's usually English, right? Because Fahrenheit freezing is 32 degrees. Celsius 0 is freezing, which makes a little more sense, right? But yeah, so English is Fahrenheit, metric is Kelvin and Celsius, because metric is based on our base 10 number system. And so it generally tends to make more sense in terms of conversions and in this case, the definition of freezing point for water. There are two conversions that I will give you on the test. However, I will not give you the form that is solved for the opposite unit. And what I mean by that is I will give you this conversion. I will give you the conversion solved for Fahrenheit. But if you need to solve for Celsius, I'm not going to give you that version. So you're going to have to say, okay, well, Celsius is equal to Fahrenheit subtracted 32 and divided by 9. Okay, I'm only going to give you this version. If you solve for Celsius, you need to be able to do that. The other version, and you can also write this as 1.8 times degrees Celsius plus 32. 9/5 is equal to 1.8. And then the other conversion is Kelvin is equal to degrees Celsius plus 273. Same thing, I'm only going to give you this version, but to solve for Celsius, all you have to do is subtract 273. So this is just going to involve some algebra on your part. I want you to convert, this is practice, convert negative 17 degrees Fahrenheit to degrees Celsius, then to Kelvin. So start in Fahrenheit, convert it to Celsius, then to Kelvin. Because we don't have a direct conversion from Fahrenheit to Kelvin, you have to go through Celsius. So I didn't get to this in class last night, and I probably won't get to it today, is the converting the delta t's. So just know that they come and see that. You can kind of work through that on Sunday, but you're going to start from scratch on that problem. In that we have to convert the temperatures then to delta t. And I'll have a problem on that on Monday, but just know that they come and see that. Okay. Oh yeah, I'm just going to send a Slack message to. What did we get for Celsius. Negative 35. Let me double check. Let's see. I have an answer here. What did everyone get negative 35 or did they get something else? I got negative 27. Yeah. So let's work on that. If I can find my, where did my stylus go? I've got another one. Okay. So let's solve this. And this is important because it's talking about orders of operations. So in order to solve for Celsius, first you have to take Fahrenheit and subtract 32 from that. Then you're going to divide by 1.8. So it's important that you don't divide by 1.8 first and then subtract 32. You need to do you have to subtract 32, then divide by 1.8 because that's your order of operations. And you should get negative 27, which if you think about your sig figs, will be specific to the one place. Divide that by 2 sig figs, you should get 2 sig figs. Negative 27 degrees Celsius. What about that in Kelvin? Add 273, you get 245 Kelvin. Is that right? That's what I got. Okay. Questions? There's one more thing I want to talk about in terms of conversions between these 3 units. If you think about the scale of Celsius from 0 to 100 degrees, 0 degrees Celsius to 100 degrees Celsius, that delta T is 100 degrees. Delta T just means change in temperature. So delta in the sciences means change. So delta T in 0 to 100 degrees is 0 degrees Celsius, right? Pretty simple. What is 0 degrees Celsius in Kelvin? $273. 0 plus 273. 273 Kelvin. What is 100 degrees Celsius in Kelvin? 373, because you just add 100 to 273. So we have 373 Kelvin. Now, what's my delta T for that one? 100. The delta T in Kelvin and Celsius will be the same if you're talking about the same amount of thermal energy. And what I mean by that is it's because they're in the same system, in the metric system. It's like they're 2 sets of stairs built by the same person. If you want to go up the one floor, you're going to go up the same number of steps. The only difference is that Kelvin has 273 degrees going down, 273 more steps going down to the basement. So you can just go lower with Kelvin, okay? But as you move up degrees, that's the same amount of gained height, or in this case, gained thermal energy. However, Fahrenheit, those stairs were built by a different guy or girl. And the steps are shorter. So what's 0 degrees Celsius in Fahrenheit? 32. If you grew up in the States, you know that pretty well. Now, I'm not going to make you do the calculation right here. I will just tell you that 100 degrees Celsius is 212 degrees Fahrenheit. That's not 100 degrees. That's actually 180 degrees difference. So, delta T, if you convert in Celsius and Kelvin, the delta T between 2 temperatures or 2 levels on a thermometer will be the same number of Kelvin or degrees Celsius. However, if you travel up the same amount on a thermometer in Fahrenheit, the number will be bigger because they're smaller steps. Okay? Review session on Sunday. I will see you on Tuesday for a review session. I will see you on Monday for a review. Sorry, I will see you on Wednesday. Sorry, for a review lecture. I will see you on Monday for a review worksheet, and I will see you on Friday for the exam. Bring your own calculator. I will not have extra ones. Don't be late. You don't get extra time if you are late.